Hi, this is Sudeep, and I welcome you back to this wonderful series of learning structure analysis with StatPro. We have now completed our discussion on the modeling of geometry and the modeling of properties and materials. Now we will step into the modeling of support systems. I would request all of you to view sessions 7, 8, and 10 of this series because the concepts I have discussed there would be needed to understand the contents of this particular session. Sessions 7 and 8 discusses the condition of static equilibrium. You can access sessions number 7 by clicking on the link that is appearing on the right side of the screen right now. Session 10 discusses the characteristics of the fixed, pinned, and roller support. You can access the session by clicking on the link that should be appearing on the screen right now. Please also note that the discussion is applicable only to planar structures, as we had been handling only planar structures during this course. Alright, but before we go forward, please take a moment to subscribe to this channel if you are new and join us in this wonderful journey of learning structure analysis with StatPro. Consider two nodes single member system. Nodes A and B have a member connected between them. Let us theoretically consider that this is a weightless system. So we can consider this to be dangling in space. Now let us consider a load on the system. Now this would result in a rigid body motion in the structure and the structure would plummet towards the ground. Now under this condition, this system or this structural system doesn't serve any purpose unless we stabilize it to carry out its function of carrying the load. Now in order to stabilize the system, let us consider that we arrange a support that would prevent the vertical motion of node A. Now, does this stabilize the structure? Note that the applied load and the reaction in the support would create a couple and the structure would now rotate about the support. So it is clear that one single reaction is not able to balance the applied load. Now let us consider that we restrain the vertical motion of node B in addition to restraining the vertical motion of node A. Now the beam stabilizes against the vertically applied load. But is it really a stable system? Well, let us see. Now what this really transforms into is a system with roller supports at both the nodes. So apparently, though the system is in equilibrium under the vertical load, this equilibrium is what is called an unstable equilibrium. So if there is a slight horizontal load to push the structure would undergo a rigid translation in the direction of the applied force. So it is seen that even the two reactions cannot stabilize the beam against a general system of applied coplanar forces. So if we have this structure and have an inclined load applied on the system, the inclined load can be thought of as one horizontal and one vertical load. While there is no problem balancing the vertical load, the horizontal load will not be balanced unless we have at least one node having a support capable of developing a horizontal reaction. So we see that we would at least need three reactions that needs to be developed to lend a stable configuration to the system against a general applied coplanar system of forces. This would translate to the following supports, having a pin support at one node and a roller support on the other, which can only provide a vertical reaction, whereas the pin support can provide both the horizontal and vertical reactions. The stable configuration is called simply supported beam with roller on one end. Now let us look at an alternative solution of stabilizing this beam. So in addition to restraining one of the nodes to move in the vertical direction, we also prevent the rotation of the same node instead of restraining the other available node vertically. So in this case, we have applied both types of reactions on the same node. The other node has been left free to move about. Now, we see that for the current loading criteria, this arrangement has lent stability to the beam. But is this system stable against any general coplanar load system? Well, the answer again is no, because if we have a horizontal load applied on the beam would again as before would translate in the direction of the applied force. So this would mean that under the vertical load, the system is in a condition or a state of unstable equilibrium. So again, we would need an additional horizontal reaction to stabilize the beam against a general system of coplanar forces. So again, even in this alternative solution, we see that we would need at least 3 reactions to stabilize the beam system against any general system of coplanar forces. So this actually translates to this system where we have restrained only one node with a fixed support while the other node is free to move. This stable structural configuration is called a cantilever beam. Now you may remember from session 7 and 8 that there were 3 equations of equilibrium to solve for the unknown reactions, and we must have at least 3 available reactions for the stability of the structures. Thus, 3 equations and 3 unknowns make the problem a determinate one. That is, we can solve for the reactions by using the available equations. So we can conclude that a stable structure has to be statically determinate. This is necessary condition of equilibrium. But is this also sufficient? We will answer that in a while. Now let us revisit the first stable configuration of a 2-node single-member system. Now instead of the roller support on the right, if we introduce a pin support, we actually introduce one more additional reaction to the general coplanar loading on the structure. This configuration is called a pin-pin beam. Now note that we have 4 unknown reactions, but we have only 3 equations to solve for the reactions. Hence, we cannot solve for the reactions on the basis of equilibrium conditions only, and we need an additional equation to solve for all the 4 reactions. Thus, this is a statically indeterminate system. Since we have one additional reaction than the equations available, this configuration would be said to have a statical indeterminacy of degree 1. In other words, the degree of redundancy in the structure is 1, or if we have one additional or redundant reaction that would be needed to achieve a stable configuration, and if any one of the reactions is removed, we will still have a stable configuration and we will be back to a statically determinate structure. Now let us look into the second stable configuration of the same system. In this case, if we introduce a roller to restrain the right node in the vertical direction, we again introduce one additional redundant reaction to the system, and the statically determinate problem changes to a statically indeterminate problem as we have one additional unknown than the number of equations available. So even in this case, the structure has a statical indeterminacy or redundancy of 1. Now, what would happen if we introduce one more roller support in the system? Well, the degree of indeterminacy of the structure would now increase to 2, meaning that we have 2 additional unknowns than the number of available equilibrium equations. This also means that we have a more stable system than the structure with the degree of indeterminacy 1. We can remove 2 reactions without making the structure unstable in this case. Now let us examine this question that we had posed a while back. Is the condition of a structure being statically determinate means that it is stable, or rather, is statical determinacy a sufficient condition for a stable configuration? Let us consider this configuration that you see on the screen. We have three unknowns here, and we have three equations of equilibrium. So this is a statically determinate problem. However, all the supports being rollers, if the structure is given a slight push in the horizontal direction, the structure would move horizontally. So this system is not a stable configuration for the general system of coplanar forces, even though the structure is statically determinate. So, though determinacy is a necessary condition for equilibrium, it is not a sufficient condition. The reactions in a statically determinate system needs to be properly configured to form a stable configuration. Now let us leave this discussion at this point. We will discuss the idea of degree of redundancy or degree of statical indeterminacy in more details later in the series, and we will also solve a couple of problems on this. But this session was supposed to be a primer before I teach you how to model supports in StatPro. The intention of this session is to make the learners understand that the constraints imposed through supports has to be done properly, else it might not lead to a stable configuration of the structure. So knowing what supports to apply and where to apply those supports is an important consideration before actually modeling the supports. In the next session, I will show you how you can model a pinned, fixed, and roller support in StatPro. If you have liked this session today, please hit the like button so that this session can be accessed by more students looking for a similar content. See you in the next session. Till then, bye bye.